This is the last, this is L5 PDF. I will upload after. We already saw that every binary relation on any set is a graph. Yes, that's right. If X is a subset, V is a set. We don't say it's finite or anything. If V is a set, then X is a subset of V cross V. Then X is a graph. Every binary, this is a binary relation. Every binary relation is a graph. And we, in fact, generalize this into set systems and relational systems in that part. Now, let us take V as any set of mathematical objects. Because I don't like the definition of a set to be a collection of objects with a common property, which is written in every book in the library. I never use that definition because that definition is faulty, it's not well defined. But here the objects are clear because we are talking about only mathematical objects. So if you want to ask me what mathematical objects are, I'm going to tell you it's finite groups, rings, geometric sets, functions, topological spaces. These are clearly given mathematical concepts. We're not saying that this word object in the same context as a collection of objects with a common property. So this is clearly specified mathematical objects. And then if you have a transformation, which is a subset, this is a transformation of mathematical objects. For example, if your mathematical objects are vectors in a vector space, then you have linear transformation, which is giving you another vector in some other space maybe. But if the linear transformation is from the space to itself and linear endomorphism, then we're getting a vector in the same space. So this is there will be no ambiguity. So we're going to take a T transformation, which is actually a subset of that. So by this, every such transformation is a graph. Every set of transformation is a graph. So this is what is called transformation graphs. And we're going to see examples. If you have read Professor Saunders Macauley's Working Mathematician, you should, if you study, sit down and study carefully. Don't just browse. The book is called Categories for the Working Mathematician. I used to remember the exact page on which it was set, but it is somewhere in between 150 and 170 page. You check it and try to find it out. He remarked there that every mathematical category has a faithful mapping into a category, some category of graphs. Actually, it's some category of finite graphs he was talking about, but it was finite directed graph. Here we are looking at directed graph because it's a Cartesian product. He said this in somewhere in that book. He wrote it, and he actually said that a category of graph contains any mathematical category can be contained in some category of graphs. He said something like that, and then please check it. It's there, and I used to know exactly which page it was, but now I forget. So now this is the transformation graph definition. So let us have a look at one example. So let B be the set of some set of finite groups. We're not even talking about category. Category of finite group is definitely one special example, but we only take any set of finite groups. We have encountered finite groups in the context of Cayley graphs. And the transformation, consider if X, Y are groups. If G, H are groups, now it's a small letter. Let us write it later. It doesn't give us any confusion. Uppercase G, H. H are in the set. You can even say that let V be the set of groups of order 100. So that is a very special set. Every group in this set contains exactly 100 elements in it. So that we are now going to have a graph of order 100. If there then F is a homomorphism, group homomorphism. Then we say that this GH belongs to the EX. So this graph will, its vertex set is a group in the set V, and the arcs are homomorphism. If there is one homomorphism, it could be many homomorphisms between them. But if there is one homomorphism from one group to another, then we have an arc. Now, if we take V to be all finite groups, non-isomorphic finite groups of order 100, one containing 100 elements, then there could be, I don't even know how many groups are there. So the V will have that cardinality, and each vertex is a group. And if there is a homomorphism from one group to another, then there is an elliptic edge. So this gives us one example of a transmorphism graph. It's a transformation graph. If V is the category of finite groups, special case is if V is the category of finite groups, this is definitely a good category. Then we have our transformation graph is the theory of groups. Isn't it? Or the category of groups and homomorphisms. The transformation graph is the theory, group theory. Because in group theory, we only study groups and homomorphisms. Of course, we also study subgroups, normal subgroups, etc. But those can be also given by means of the homomorphisms, right? So, this is one example of a transformation graph.
The first example here, divided by GH, it should be belongs to edges of V or edges of X.
Edges of X. X is the graph. The V is the set of mathematical objects.
G is the vertex.
So, what is the X?
X is the graph, which has various vertices, set of vertices, and
Fine.
those arrows as edges.
Just binary relation on defined.
Yes, it's a transformation.
Okay.
The transformation in the case of finite groups is homomorphisms. Of course, it includes isomorphism as well. Thank you for the question. I have to have a look because I don't want to diverge. What did I bring? examples. We have to work on examples. Second example, let us consider the mathematical objects to be integers. So let b be equal to z. When I write z, it is a ring of integers. It is the ring of integers. It has two binary operations. Under the addition, it's an abelian group. Under the multiplication, it is
Monoid.
a monoid.
Commutative monoid.
Commutative monoid if you don't include the zero.
Yeah.
So even multiplying by zero is also allowed.
Yeah.
So this is integers, and then we define x. Define a transformation graph. This is now giving us a very specific thing. Define the transformation graph x with v as vertex set, and we're now going to define the x set. E equal to xy. Xy are integers, and x divides y. Y is a multiple of x. What do we get? We get number theory, elementary number theory, which concerns divisibility, and divisibility part and congruence part is there. And now I'd like to it doesn't have to be, B doesn't have to be the all of Z. Now let us consider any non-empty subset of Z. So let B equal to start with 2 and stop with 20. This is a subset of Z, right? We're only looking at divisibility in that set. Now I'm going to work together and draw the graph so that we can. Mathematics is, in my opinion, it's a personal thing. If you go social, you usually don't get mathematics. And mathematics, in my opinion, is also a goddess who is at least 3,000 years old. And she's still a child. So you should really respect, even if you respect, she will discard you. You have to be persistent and following her, and then you will get something very beautiful. Let us have a look at, put our hands on it. You have to put your hands on the mathematics. You have to have it as your own. So let us look at that set, 2, 3 to 20. Let us put 2 here, 3 here, 5 here, 7 here, 11 here, 13 here, 17 here, 19 here. And then we put this is ordered there. Put the multiples above the numbers which divide them. So let us have a look at who are the multiples of the 4 will be somewhere here.
Yes, sir.
From 2 to 4 there is the edge, and it is going up, so I don't need to draw the arrow. The up direction is arrow. And the 3 is not joined to 4 because 3 doesn't divide 4, right?
Yes. Hash diagram.
Eh?
Hash diagram.
Hesse diagram. It's called Hesse diagram.
Yeah.
I don't know what Hesse diagram. I know what Hesse diagram is, but it is, yeah, it could be Hesse diagram, but this is our transformation graph for divisibility. And 6 is somewhere, right? 2 divides 6.
Yes.
3 divides 6. Others don't. And what does 4 divide?
4 divide 8.
8. And then 8 is also, 8 is up there. I should really now display because I have it already drawn. Now 5, on top of 5 there is 10.
10.
Which is also joined to what, 2, right?
Yes.
Yeah.
On top of 7 we have 14.
14.
14 is also joined to 2.
So,
We missed 12.
We miss 12.
Yeah.
But 12 is here.
yes.
Yeah.
12. And 12 is, if 3 divides, then divides through 6, we don't need to draw that edge.
Mm.
And we have from 4 to 12.
Yeah, the immediate division. The Hesa diagram has those edges. And then 4 to 12 is an edge.
Yeah.
On top of 10, we have 14 there, and then now we have 15.
3.
13 is already here, so 12, 13, 14, 15. 15 is a multiple of 3 and 5. That should have drawn it somewhere else. This is why I am doing this. I have the graph drawn already. So let us put 15 somewhere between there. 3, 5, 10 doesn't divide. 16. 16 sits on top of it. Any other division of 16, 8 is there, so it goes up that way. 17 is here. 18 is somewhere there. 18 is a...
And 9 is 9.
18 is divisible by 6.
9 is missing.
9 is somewhere. 9 is below 12.
Yes.
Somewhere here. Okay, let us redraw 12. 9 and this is 9. But this is 12. 9. This is 12. This is 9. 9 is divisible by 3. 18. We now have reached 18, 17, 18, 19, 20. There's only 20 remaining. 20 is on top of 10. So you by just, I think a child can do this, if she understands this line already. And then by doing this, you really feel the graph, feel the transformation graph coming out. So this is called divisibility graph. Some people pay names. Why are we interested in transformation graphs? There are 3 good reasons. One is it's general. It includes almost every part of mathematics. So the number one reason is that it is general. If we can't do things in general, we rather do things in general. Secondly, it is not quite studied enough. Fairly new. Young girl. Fairly new. Thirdly, its structure depends on mathematical objects, the structure of the class of mathematical objects, which means it can be easily understood that if we have to study geometric sets in transformation graphs, we might have an advantage. That is what my reason, 3 reasons are. Geometric sets. We are going to define geometric sets in the next lecture. Can be studied with help of the set V. Set V, remember that it's a set of mathematical objects which has lots of nice properties. For example, groups. You cannot really have 2 arbitrary structure in the category of groups. Even divisibility graph here, for example, what will be bisector of these 2 points? That is a kind of a geometric question we're going to ask. if you take these 2 points, this is a metric space, and of course it's not connected because unless you have one here, all primes will form an anti-chain, infinite anti-chain. If you put one there, all primes are still infinite anti-chain, but the whole graph can be connected. So you can add one, and then you introduce all these edges so that the graph becomes a metric space, no problem. Now it is a metric space, and you can consider, for example, what is the bisector of these 2 points. Of course, 1 is in it because its distance is equal to both 1, 2, 5, and 7, and 14 is in it because of those 2 edges. I think that's about all. Because, of course, there will be points which are distance 2 to both of them, and 3 to 1. You have to check through that. Now, another thing is if you take a finite part of this divisibility graph, particularly if you take a finite subset here, then you can program an experiment. That's the advantage of this. If you do enough experiments, like a chemist, you might be able to see something. We are so much discriminated, the mathematicians. If you do one experiment in chemistry, and if the result is somewhat new, and then you publish, its impact factor is 5.75 or 7 point something. Just one experiment result. If you do one experiment like what we just already did, you cannot even publish this in mathematics. How unequal the human society is. For chemists, you do experiments, and in one experiment result 7 others. Impact factor 7 point something. Impact factor. I think if Fermat lived today, he would not be a mathematician, he would be a professional lawyer only. If Fermat lived today, his things would never be published. Because he didn't work in a university or research institute, he doesn't have research grant, he was completely on his own money. But how Fermat impacted mathematics, you have to see after 370 years. So now this is a third example of a transformation graph. I don't think we have to give too many more examples. Oh, another one. I now remember. Let us consider the fourth example. Let us just draw graphs. You need to recognize this graph and tell me what it is. That is your task. Do you recognize this graph? The other one I will draw first, and then you will think about it in the meantime. What is this has a name, and what is it?
Right.
Who is it? Thank you. This also has a name of it. So you said bipartite, so I will write it. Give you credit. You are the author of this. This case is this one. You have to, when you start drawing graphs again and again, you see that there are so many different beautiful ways of giving one graph. This is the third one, because we have drawn 2 of them already. That one is K2 direct product with K3. K3 is there, and K2 is there. Now, the transformation. What does it do? It takes away these 2 edges and then put them back this way. Or you take these 2 edges and put them back that way. What is the transformation graph here just for these 2 graphs? The transformation graph is K2. One vertex, 2 vertex, they are adjacent to each other. You see, you can get transformation graphs from mathematical objects called graphs themselves. Now, this seems to be too easy, and if you submit it, it will be rejected by on the reason that it is too easy. Now, let me ask just a bit slightly more not easy question. Of course, with 6 vertices, there are exactly these 3 regular graphs, cubic graphs. On order 8, there are 5. Question? On there are exactly 5 3 regular graphs of 8 vertices. How many are there on 10 vertices? Oh, let me ask you another silly question. How many of 3 regular graphs are there on 7 vertices? Anybody can answer?
3 regular graph on 7 vertices?
Yes.
I don't feel such a graph will exist due to handshake.
Thank you very much, Muhammad, because that is what I wanted to hear. Because in any graph, by Euler's theorem, the number of odd degree vertices is even.
Yes.
So that for 3 regular graphs, you only have them on even order.
Yes.
What is the smallest even order on which you can have 3 regular graphs? It's 4, because you have to have 3 neighbors for
Yes.
some vertex. And which is K4. So the 4 gives you K4. 6 gives you these 2. 8 gives you 5. 10 gives you, I forgot the number, it's at least 10. 12 gives you something like several dozens. 14 gives you, hundreds. 16, 18, and goes on. When you reach 20 to 24, you cannot even know. When it reaches something like passes 20, at least passes 28 or something, we don't know the number. We don't know how many are there. Now, if you take a cubic graph, my next question from this very simple, easy question. If you take a let V, the set of 3 regular connected graphs, cubic, it does not be cubic graphs of order 2n with n the natural number. What is the transformation graph like? Determine the transformation graph. Under such operations, so every time you take 2 edges, and then let us just say it takes 2 independent edges, and you swap it like that. Under this one single operation, what is the transformation graph like? Anybody can answer it quickly? If not, this is an open question. Even for 3 regular graphs, the transformation graphs are not well studied for this particular transformation. Of course, there are other transformations under which even I studied some. So this is a very interesting question, because if you know that, if you prove that this graph is connected, for example, then what is the benefit of that in real life? But real life to me is also mathematics. There is a good benefit in real life. If you know this transformation graph and this operation is connected, what is the benefit? You know it, I think. If you know any one of them, if the transformation graph is connected, then using a computer I can find all of them. That is the benefit in real life. Still within mathematics. We don't need to go to chemistry. So transformation graphs are very interesting. Not well studied, and because of it having set V having some mathematical properties, it could help study the geometric sets inside. Our mini course, the main theme is geometric sets. So we only go around this theme. because we don't want to, although I'm introducing too many things, but we want to go around that theme, that topic, which is called geometric sets. Now, I'd like to address what is called invariance. My colleagues are not here, so let me tell you, there was an interview. The interview, there were lots of people whom we would really like to take. The postdoc interview, I was there. I was also asking questions. I wasn't asking questions. The other guy from LUMS asking all the questions. And I told him that if you are interviewing me, I would be very happy because we will have a seminar running for 1 week if you keep on asking questions like this. And then he somehow stopped asking questions. But one of the questions he asked was, can you tell me in simple words what a graph invariant means? The girl didn't answer, didn't even know. Graph invariant. So we are now going to rigorously define it, and this definition is, in my opinion, random, because all the current description of graph invariance doesn't come to this point. So let me now define